Hello, my lovely statisticians. I'm sorry I can't be there today. We are going to go into Chapter 21 a little bit more. We didn't quite finish our notes last class, but we'll do that on Wednesday or Thursday, depending on what class you're in. So for now, what I would like for you to do is pause the video and actually try the warm-up. It's from Chapter 20, so if you need to use your Chapter 20 notes, you can do that. When you unpause the video, I will have answered the warm-up, but I want you to try it first. Feel free to use each other, ask for help. Take about 5 minutes to do that, and then you can unpause the video and watch the rest. All right, folks, so hopefully your null hypothesis looks something like that, where you have like P1 equals P2 or PM equals PW. Again, the alternate version of this, not the alternate hypothesis, but you could do PM minus PW equals 0. That also works, same idea. And then your alternate hypothesis would be PM minus PW is greater than 0. For part B, you have to check all assumptions and conditions. So we randomized, we are less than 10% for both men and women. The genders are independent of each other, and then make sure you calculate both success and failures. So it's 47, 175, 37, and 171 are all greater than 10. For part C, you can just put in that proportion into a calculator and get the z-score, which was 0.78, and your P, your probability, is about 22%, which is greater than 5%, meaning we fail to reject. And you should write a little note about what that means. So in our case, it would be there's no evidence that men are more likely to buy books online. Okay, so what you should see is that the chi-square test of goodness of fit is a test that it tells you whether the counts in categorical data, so I would actually circle that, matches the distribution predicted by a model. So what that means is if you're looking at data, does it fit that standard of what they assume it will look like? So the test finds a p-value, you look at the chi-square model. Usually, again, it's n minus 1 degrees of freedom like we're used to. N is the number of categories this time, though. So that's kind of the new part. Okay, I'm going to have you take a minute and just pause the video again. I want you to read through the scenario. They're talking about birth month and, excuse me, related to being successful as a CEO. And then they also want to figure out if that's related to baseball. So I want you to read through and just see the scenario. It says, well, how can we find the expected count? So basically they're having you look through and see how they figure out the expected numbers, and I'll go through that in a second. But just pause through the video and read first. Okay, so again, I want you to see, you can look at the ball player count and look at the month and all that. But the big thing to look at is the percent for the national. So they're saying that 8% of people are born in January, basically. So to figure out the expected values for those, basically the 118.24 they got because they took 0.08 and they actually multiplied it by the 1478, so 1,478. So notice that they're taking the total, not the individual counts, and multiplying it. I just wanted to clarify that for you. And that also means that for the second month, they took 0.07, because notice in the second month it's 7%, and it's multiplied by the same number, it's 1478. So just be careful on that. They explain it here, and you can feel free to read why. Again, they don't round because the expected values don't need to be like people right now, but we'll go on a little bit more with that in a little bit. All right, assumptions and conditions. So a lot of these are the same as what we've done. The new one here that I slid the box away for you is counted data condition. Again, they have to all be counts, so not proportions, not means. So again, counted data condition. The independence assumption is really similar to what we've already looked at. So all the cells have to be independent of each other. Randomization you should still do. 10% condition we still have. The expected cell frequency condition. We actually talked about this already. It has to be at least 5 in each cell. And again, it's really similar to what we've seen in the past. So that's not really new to us. All right. Our next example, they're talking about professional baseball players who are more likely to be born in the same month than in others. We've observed the expected counts for the 1,478 players. So they actually just showed you what the assumptions and conditions look like in that situation. Again, you can take a sec to read through that, but the big one here, again, is that you need to have at least 5 of these values in each cell, and in this case they have in like the hundreds, so we're totally fine. Again, our class's data was a little bit off because of that, and it actually screwed up our chi-square analysis a little when we did the tongue and ear data. In fact, we were supposed to take 36 and multiply it by each of the predicted values to find the expected, but our values were messed up because of me. I was the only person that couldn't roll their tongue and had the attached earlobes. So anyway, so we've already done this. We've used this formula already. You can find the chi-squared by individually calculating your observed minus expected values, squaring them, divided by expected, and then add them all together. This is your test statistic. It's called the chi-square. All right, so the number of degrees of freedom for a goodness of fit test is still n minus 1, but in this case you're looking at categories, not the number of values. So the example that they used was talking about months. So your degrees of freedom would be 11, because if you subtract 1 from 12, you end up with 11 back. Then they took each of the expected values and subtract them from the observed. So if you look back at the table, again, they said they got it by technology, the chi-square value, but you can plug that into the formula too. Remember, you could always plug in your observed data into L1, your expected values into L2, and then do the work from there. So the other thing I want you to notice is that the graph looks a little different. This is a chi-square distribution instead of a normal model or T-chart. Again, it's talking about the data and how far away it is from 0. It's kind of like when we were doing differences. I won't really make you graph that. Again, the p-value you can get from your calculator. If you're using data, like we did today, you want to use the chi-square goodness of fit. From data, okay? If you're given a two-way table, it's just your chi-square test. Okay, so they're a little bit different. And then again, all those same rules apply. So they said because of the p-value being really small, they reject the null hypothesis, saying that there's evidence that the birth rates or the birth months for Major League Baseball players have a different distribution from the rest of us, which is kind of funny. And again, you could also use the critical value on the back page of our notes that we looked at last class. So that's where they got the 19.68. You could also check that. So they looked at the table, looked at the degrees of freedom, which was 11. And then that's just another way to support that you rejected your null hypothesis. All right, I'm going to have you try something with your partner. If they're in a different spot than you, just give them a second, and I'm going to have you guys run through the calculator. The directions are right here. Again, it's kind of like what we did in class yesterday, but they want you to do everything in there. So I'm going to have you try to follow the directions and see if you can get it. I can always go through this with you next class too, but these are your observed counts. Again, it's a goodness of fit test. You're going to do what we did last class with the L1 and L2, degrees of freedom. Your expected value is actually going to be 1/12 times the total that you get from L1. So what you actually want to do is, you can just do this on paper, especially because it's a small amount of values. You want to add these up together and then multiply it by 1/12 in each of those categories. Okay, so if you want to make L3 that column, it's not each of those individual counts times a 12th. It's actually your total of these, so it's the sum of this, times 1/8 for each of those then they put it in L3 for the values. Okay, so for example, I can kind of do it out for you. Basically, if you add all those numbers together, you end up with 256. So instead of, they put 1/12 in L2. Instead, what you could type in L2, if you go up to the top of it like we have been doing, and make sure it's highlighted, if you literally just do 256 times 1/12, and then that is the entire column, you can just keep doing that down. That's what each of those values are for L3. So you actually get the same values. I would put it in L2 actually, so you would put that in for each. So again, that L2 column, or your expected frequencies, are the same number for all of them, because you're taking your total from L1 and multiplying it by your expected value, your predicted value, which is 1/12. Because you are predicted to be born on any month, the chances are 1/12. Okay, so then L3, you can do what we did before and do L1 minus L2, and again square it, again like exactly what we did last class. Again, I can go through this with you next class if you're struggling. But I wanted to clarify that for you, because I think last class we were multiplying by L1, but really you want to do the total from L1 and multiply it by your predicted values. So run through this with your table partner. Again, if you're struggling, I can help you next class. Okay, significance in a two-way table. So I just wanted to remind you that the expected counts are a little different when it's a two-way table. You want to do row total times column divided by grand. And your degrees of freedom are a little bit different. It's row minus 1 times column minus 1. Okay, that's your degrees of freedom for that case. Okay, so I'm going to have you try this example. We kind of did it, a similar kind of question last class, but I want you to see if you can get just the observed counts first. You can answer 9 and 10 while you're at it too, but again, figure out what that table would look like if you plugged in the values, and I will show you the answer in a few minutes. So just pause the video, see if you can figure this out without my help first, and then I'll show you the answer. Alright, so it helps if you fill in the table a little bit. So what they said in the question is that suppose all 125 beetles survived. So really they're giving you that total on the end, so this is 125. So if you're trying to figure out your expected value for that, so it says what's the expected count in the first cell. The reason they got 50 is it's 125 times 200, and you're dividing it by 500. So you don't even really need to fill in the table itself. Hopefully you figured out your degrees of freedom was 2, because it's 2 minus 1 times 3 minus 1, and then multiplied. And then 13, it says if it turns out that only 40 of the beetles in the first container survived, what's the calculated component of chi-squared for that cell? So again, that you're just using the formula for it. My niece Chloe decided to wish you good luck on this question, so I threw her in there. So you want to do your use your formula for that, which is again your observed, which they said only 40 beetles survived, so you do 40 minus your expected would be that 50 that you just calculated. You're going to square it, divide it by your expected, which is going to be again 50 just for that cell, and that would be your value. So if you do that, that's 100 over 50, which is 2. So that would just be for that cell. Remember, when you do a full chi-square test, not just for that one cell, which is this one, that's what they're talking about, you have to add them all together. Okay? Alright, and then the last thing that we're looking at, we actually did this last class too, so I'm going to have you kind of do this on your own without my help again, but you're now putting this data into a matrix. So they wanted you to use Hopefully you can kind of see the data that you're using there. But they're having you use a 3x2, which is actually okay. And again, you're just typing that under your matrix button. So if you can help each other out, that would be awesome. They gave you what those are actually calculated for you, so you can just copy what they gave you on the paper that you have in front of you. And again, try to run through it without anyone's help, but if you need help, help each other out, please. So again, see if you can figure out what that means in terms of the chi-square. And I will have you ask me tons of questions tomorrow if you still need help. If you are all done with the video, then you can start to work on your classwork. You will have no homework tonight if you do that in class and hand it to the sub.